All right. Good morning, everybody. Welcome back to Hillsdale. Those of you who are traveling for Easter, and welcome back to Calc 2. Plan for today: we're going to finish off Standard 12 in class. Talk some more about the integral test, which we talked a little bit about last, like a week ago, but haven't talked too much about yet. Got my usual office hours today from 11 to noon and from 1 to 2, as well as tomorrow from 1 to 2. And as far as homework goes, don't forget, we've got an exam this Friday over standards 1 through 12. Also, there's a homework that's I posted a week ago that's due on Friday as well, and we'll have our standard 12 quiz on Monday. So, lots coming up, lots to do. So, I updated everyone's mastery totals yesterday on Canvas, so they should be accurate. I think I've gotten everything graded. If you feel something is missing, please let me know. So you should know where you stand going into this Friday's exam. As a general rule of thumb for the exam, just as a reminder, there'll be one page on every standard from Standard 1 through Standard 12. If there's something you have 2 masteries in, I recommend you skip it. If you have any standards that you're still not feeling confident on, you don't be afraid to skip those as well on the exam. Kind of focus on the ones you feel ready for. So for instance, if you still need masteries in 10 different standards, it might make more sense to pick out 6 or so, 5 or 6 that you want to spend your time Friday testing over, just so you make sure you have enough time to focus on each problem. I've generally found that students who try and do too many standards end up on an exam tend to end up getting fewer masteries than they would if they had just picked out several that they really want to focus on during exam time. Well, that's just me. You can, I'd be happy to meet with you to talk to you about anything in the meantime. But otherwise, it's up to you to develop your own strategy going into this Friday's exam. Any questions or comments before we get going? One other thing I forgot to mention is I went in yesterday on Canvas and I updated it, so I've been falling a little bit behind on posting my notes and quiz solutions and such, but everything should be up to date as far as copies of packets, my own notes for various packets, and in-class quiz solutions. So encourage you to check those out if you want to pick my brain virtually, so to speak. And with that, 3 statisticians are out hunting one day. They're out duck hunting. When suddenly, a duck passes overhead. First statistician brings out his gun and shoots. He misses. He was 6 inches too high. Second statistician, she pulls out her gun and she shoots. She also misses. She was 6 inches too low. Third statistician immediately pumps his fist and says, "Yeah, we got him!" Because on average, their shots were perfectly accurate. So something about precision is key in statistics, not just overall that your average result matches up. And with that, let's get back into talking about the integral test. So for Easter, we had talked a little bit about some of the different tests that you can use to determine whether or not a series is going to converge. We talked about the geometric series test. If you have a geometric series that's of the form sum from, say, n equals 0 to infinity of r to the n power, that's going to converge to 1 over 1 minus r if r is between -1 and 1 and diverges otherwise. That was our geometric series test. So if you were adding, for instance, 1/2 plus 1/2 squared plus 1/2 cubed plus 1/2 to the 4th, etc., that would actually converge to 1 over 1 minus 1/2. We talked about the divergence test. which basically says if the individual terms you're adding up in a series, if a sub n does not converge to 0, then the sum from, say, n equals 1 to infinity of a sub n automatically has to diverge. So if you're adding up a bunch of individual terms, and the individual terms are approaching, say, some number like 1, for instance, other than 0, then that series is automatically going to have to diverge. The only way a series could possibly converge is if the individual numbers that you're adding up are getting closer and closer to 0 as n gets bigger and bigger. And those are kind of the two series tests that we looked at in Standard 11. What we're focusing on in Standard 12 is this new test called the integral test, which allows you to determine whether or not a series is going to converge by converting it into an improper integral. With the idea being, if you have a positive, decreasing, continuous function of x on some interval from m to infinity, and you have a sequence that's defined by looking at like a sub 1 is f of 1, a sub 2 is f of 2, a sub 3 is f of 3, and so on, then you can determine whether or not your series converges by instead looking at changing your n's to x's and looking at an improper integral from m to infinity of that function. And if that improper integral converges, then the series converges. But if the improper integral diverges, then the series will also diverge. So as a quick example, to get everybody back on the same page, because I know it's been a while since some of you probably thought about this. Look at the sum from n equals 1 to infinity real quick of 1 over n cubed. We want to see if this series converges. This is not going to be a geometric series because you're not taking a constant to the nth power and summing from n equals 1 to infinity. Instead, you're taking n to a constant power. So we can't use our geometric series test. I don't think our divergence test really helps us with this one because the individual terms that we're adding up, if we look at 1 over n cubed, Mary, what's happening to 1 over n cubed as n gets bigger and bigger? Or as n goes to infinity? Yeah, it's going to approach, it's going to go to 0. Side note, Mary, what happened to your row here? My goodness. Yeah, so this gets smaller and smaller, so it does go to 0. That doesn't necessarily mean the series is going to converge. It just means the divergence test doesn't tell us anything. So instead, let's look at our integral test. Where with the integral test, instead of summing from 1 to infinity, we're going to integrate from 1 to infinity instead. The function that we would get if we took 1 over n cubed and then converted our n's to x's. Take the integral from 1 to infinity of 1 over x cubed. This is a function that is going to look something like this. And we're trying to determine if we want to take the area under this thing from 1 to infinity, are we going to get a finite area, meaning this integral converges, or are we going to get an infinite area, meaning the integral would diverge? Gabe, what do you think? I remember a week ago in our last class, my how time flies, you had made a comment about, seems this is somehow related to p integrals in some way. What do we know about this integral?
We know that it converges.
Because it is a p integral with...
Right, with p greater than 1.
Yeah, this is going to converge as a p integral, with our p being equal to 3, which is a value greater than 1. And if this integral, the integral of 1 over x cubed from 1 to infinity, is a convergent integral, Joy, what does that tell us about the sum from 1 to infinity of 1 over n cubed?
It goes to a finite number.
Yeah, it's going to go to a finite number. So in other words, it's going to converge. By the integral test. So this is kind of interesting, because if you look at our graph, what we're essentially doing is we're trying to add up f of 1 plus f of 2 plus f of 3 plus f of 4, taking, if f of x in this case is 1 over x cubed, then the sum that we're really adding up here is going to be f of 1 plus f of 2 plus f of 3 plus f of 4. And in order to determine whether this sum, f of 1 plus f of 2 plus f of 3 plus f of 4, and going on forever, whether or not this sum comes out to a finite number, whether it converges or whether it blows up and goes to infinity, we can actually determine that by looking at the area underneath this graph from 1 to infinity. And if this area comes out to a finite number, then this sum will also come out to a finite number. And vice versa. If this area turned out to be an infinite area under the curve, then adding up the value of the function at each integer, f of 1 plus f of 2 plus f of 3 and so on, would also be like an infinite sum, a sum that would diverge towards infinity. Yeah, Bethany?
So when we talk about like adding up the areas, like that's different from adding the sum. So we couldn't like basically say that like the sum actually converges to that number that we get using an integral test because of the fact that area is different than sum.
Yeah, that's absolutely correct. One thing the integral test doesn't say is that these two values have to come out to the same thing. So summing up f of 1 plus f of 2 plus f of 3 plus f of 4 and so on here isn't necessarily going to give us the same number as the number we would get from trying to evaluate this improper integral. But what the integral test does tell us is that if this came out to some finite number, then this sum would also have to come out to some finite number. Not necessarily the same number, it doesn't have to converge to the same value, but this going to a finite value means this will as well, and vice versa. Yeah, that's a good observation, I think. So actually finding out what this sum is equal to is actually a pretty hard problem. Like, we know that 1 over n cubed, so 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed, comes out to some finite number. We're pretty confident. Knowing what that number is, pretty difficult. We can evaluate this integral. That wouldn't be too hard using standard 6 techniques. But actually, knowing what this number is a lot easier than figuring out what that finite number is going to be equal to. A.
So when we take the integral test and it diverges, does that give us an inconclusive result, or do we know that it diverges?
Nope. If you find that your integral is a divergent integral, then the series is going to have to automatically be divergent as well. So if and only if in mathematics is usually a phrase that means like a two-way equivalence. That if this converges, then the right-hand side has to also converge. But if the right-hand side converges, that also means the same thing as if the left-hand side converges. So if and only if typically means either both are going to be true or neither is going to be true. So in this case, either both the infinite series and the improper integral are both going to converge, or they're both going to diverge. There's no scenario where one converges and the other diverges. Yeah, good question though. Anybody else? So let's see if we can generalize this example. And Dave, you said something earlier about p integrals. Turns out we can generalize the idea of a p integral pretty easily to talk about what a p series is. So I'm on page 2 now in the packet for those of you following along there. So when we look at a p series, what we're generally looking at is going to be a sum from n equals 1 to infinity of 1 over n to the p power. So that's 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p, etc., going on forever. So this gives us another type of series, sort of like the geometric series, except in the geometric series, you would have something like 1 over p to the first plus 1 over p squared plus 1 over p cubed plus 1 over p to the fourth. This time, the p value that we're going to get is in the exponent rather than in the base. So my question is, for which values of p does this converge? In other words, if we were to plug in a value for p here and take the p series where p is equal to 5 or 10 or negative pi, how can we tell if we're going to get a convergent series or a divergent series? Jonah?
I have a guess.
What is your guess?
All values that are greater than 0?
It's going to converge for all values p that are greater than 0?
Yes.
Why do you say that?
Well, if it's 0, then they all come out to 1, and then that would go to infinity. And then if they're negative, then they get placed in the denominator, I think. Yeah, so then they would be just regular constants that are not fractions. So that would also go to infinity. So I'm assuming everything else is fine, I think.
Yeah, so I think you're onto something. So if we plugged in p equals 0, this would be 1 over 1 plus 1 over 1 plus 1 over 1 plus 1 over 1. We'd be adding 1 forever. So if p is equal to 0, this is not going to converge. If p was something negative, like say p equals negative 2, then we'd be getting something like 1 squared plus 2 squared plus 3 squared, etc. That feels pretty divergent to me. So I think we can immediately say, kind of going along with what you're saying, if p is less than or equal to 0, the sum from n equals 1 to infinity of 1 over n to the p is going to be divergent pretty quickly. Unfortunately, it's not quite as simple for values of p that are greater than 0. Turns out, if p is greater than 0, sometimes it will converge, sometimes it will diverge.
Okay.
Well, that's a good observation, though, John. I'm glad you made that. So let's see what happens if p is greater than 0. So if we wanted to look at the sum from n equals 1 to infinity of 1 over n to the p, I claim this is going to converge is the same as saying that the integral from 1 to infinity of what function would have to be convergent? If we were to use the integral test on this, what function would have to converge in order for 1 over n to the p to be a convergent integral? Phoebe?
Would it be 1 over n to the p and p is greater than 1?
The function we're looking at is not going to be 1 over n to the p, because we need a function in terms of x. So what would be our function in terms of x that we would have to look at? Aiden?
1 over x to the p?
Yeah, it's going to be 1 over x to the p. So just like we did over here, if you want to determine whether some expression like in terms of n is going to give you a convergent series, you can convert your n's to x's and see if the corresponding integral of 1 over x is going to be convergent. So here, 1 over n cubed became 1 over x cubed. So 1 over n to the p can become 1 over x to the p. So in order for 1 over x into the p to have a convergent series, we know that 1 over x to the p has to have a convergent integral from 1 to infinity. Here's the test. Does anybody remember from Standard 6? What has to be true about p in order for this p integral to converge? Bethany?
Doesn't p have to be greater than 1?
Yeah, p has to be greater than 1. So the answer to the question, for which values of p is our p series going to converge? It's going to be converge, let's write this, let's make some space on the board. My eraser. What we can actually say is that the sum from n equals 1 to infinity, 1 over n to the p, is going to converge if p is greater than 1, and it's going to diverge if p is less than or equal to 1. So you almost had it right, Jonah. It just turned out that the condition was p needed to be greater than 1 for it to converge rather than it being greater than 0 necessarily. By the way, this double arrow means these are equivalent things, meaning this series converging means the same thing as this integral converging, which means the same thing as p is a value greater than 1. So, in other words, if this converges, then this has to converge and this has to be greater than 1. And if p is greater than 1, then this integral converges, which means this series converges. And this p greater than 1 condition for the integral to converge, that's something we did back in Standard 6 100 years ago. Give or take. Almost 100 years. Any questions or comments about what this test is saying? In that case, let's look at a couple examples. So if we go move on to the next page in the packet, do the same. Let's see if let's look at some series. See if we can determine whether or not they converge using this condition. So to start with, let's look at a sum from n equals 1 to infinity of 1 over n. Fairly straightforward one. That gives you 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and etc., etc. And it go on forever. So here's my question. Is this integral going to be convergent integral or a divergent integral? No one wants to talk about this, so my students are leaving the room. Phoebe, what do you think?
Would it diverge because P is essentially one?
Yeah, we could say that this is going to be a p-series with p, in this case, is going to be equal to 1. Because you can write 1 over n as being the same thing as 1 over n to the first power. So 1 over 1 to the first plus 1 over 2 to the first, 3 to the first, 4 to the first. You can kind of plug in an exponent of 1 in each of our denominators here. And if p is equal to 1, what does our p-series test tell us? Well, it tells us that the infinite sum is going to be divergent. So the series diverges. Man. This column's dropping like flies. So in other words, 1 plus a half plus a third plus a fourth plus a fifth going on forever is going to actually be a sum that diverges. It's going to get infinitely large. It's not going to converge to any single finite number. Which is interesting if you think about it, because this is another example of one of these series where the individual terms, the a sub n's that we're adding up, are approaching 0. If we look at the sequence 1 over n, as a sequence, that does converge to 0. And yet, the series is still going to be divergent. So, kind of goes to show, looking back at the divergence test for just a second, we could say if the individual terms we're adding up do converge to 0, then adding up all of those terms may converge or diverge. The divergence test just doesn't tell us anything in this condition where the individual terms we're adding up do go to 0. Here's an example where we're adding up a bunch of terms that do go to 0, but the series still manages to diverge in the end. By the way, does anybody know what the name of this series is from, say, like a physics course or some other class? The series has kind of a famous name to it. Okay?
Simple harmonic.
Yeah, it's a simple harmonic series, or I'm just going to call this the harmonic series. Turns out, looking at properties of this series has a lot of useful physical applications to it. That we're not going to dive too deep into in this class, but this one is fancy enough to have a name. Let's do another one. Very similar sum, except I'm going to tweak it. So instead of just being 1 over n, we're going to take 1 over n to the power of 1.0001, which is the same as taking 1 over 1 to the 1.0001 plus 1 over 2 to the 1.0001 plus 1 over 3 to the 1.0001, etc., going on forever. So this is going to be another p-series. Kate, what's going to be the value of p that we get looking at this particular p-series?
The value of p would just be 1.001.
Yeah, in this case we can say that this is going to be a p-series with p is equal to 1.0001. And if we have a p-series where p is equal to 1.0001, Maria, is this series going to converge or is it going to diverge?
It'll converge.
Yeah, this series is going to converge since p is greater than 1. Which, if you think about it, it's really, really weird. At least it's really weird to me. Because these look very close to being the exact same series. The only difference is instead of having exponents of 1 in the denominator, we're tweaking the exponents of the denominator very, very slightly to be 1.0001 instead of 1. And yet that very, very slight tweak is enough to make it so that this series goes to infinity, whereas this series actually comes out to a finite number in the end. How to find out what finite number this series comes out to is a very difficult problem, and one I'm not going to ever ask you to do. But we know that this series comes out to some finite number, the series converges to something, whereas tweaking the exponent ever so slightly makes the sum go off to infinity instead. So it doesn't converge to anything. Holy moly. Any questions or comments on this one? Alright, let's spice things up a bit then. Let's look at our integral test room. Let's look at a sum from n equals 1 to infinity of 1 over n squared plus 1. No, I guess I had it as k in the packet, fine. So that's going to be 1 over 1 squared plus 1, plus 1 over 2 squared plus 1, plus 1 over 3 squared, plus 1, etc., etc. So that would be like adding up 1 plus a fifth, plus a 10th, plus a 17th, etc., etc., going on forever. Is that going to come out to a finite? Is that sum going to converge to a finite value, or is it going to blow up towards infinity? Reagan, if you had to guess, would you guess that this series would converge or diverge?
I guess that it would diverge
Why?
because you just keep adding more numbers onto it, so it's gonna keep going closer.
But isn't that the case with every series? That every series you're going to keep adding more and more terms, infinitely many terms together, say?
Yeah.
So, I don't know if that works as kind of our reasoning for saying that this series is going to diverge. Carson, is this series on its own a p-series? Well, let's look at the individual terms. Are the individual terms just 1 over, in this case it'd be k, 1 over k to some power? Or do we have something else going on with these terms? What else is going on? Yeah, this plus 1 in the denominator makes this a little bit of a sticky wicket, so to speak. So this is not itself a p-series. It kind of looks like one though, doesn't it? Carson, do you agree? It kind of looks like 1 over k squared or 1 over n squared. Intriguing. So we can't just straight up use our p-series test. So let's instead convert it to an improper integral and see what happens when we look at that instead. So what we're going to do is we're gonna take our sum of 1 over k squared plus 1, and instead, let's look at our integral from 1 to infinity of 1 over x squared plus 1. So as x gets bigger and bigger, this is going to get closer and closer to 0. So we have one of these sort of type 1 improper integrals that we're going to have to look at. How do we determine whether or not this integral is going to converge or diverge? Bethany?
Well, the integral of this is the inverse tangent expression,
Bethany, are you trying to introduce inverse trig functions back into this?
Yeah.
So there's actually two ways to go about this. One that involves inverse trig functions, and one that doesn't involve them at all. Bethany has chosen the path of pain. Okay? Sure. Let's convert it. Let's do this with inverse trig to start with, just for funsies. So this is going to be the same as taking a limit as r goes to infinity, integral from 1 to r of 1 over x squared plus 1. As Bethany pointed out, we can integrate 1 over x squared plus 1 by using an inverse tangent function and just say, hey, 1 over x squared plus 1, that's the derivative of inverse tangent of x from 1 to r. Which we can plug in r, plug in 1, see what happens. We'll get a limit as r goes to infinity of inverse tangent of r minus inverse tangent of 1. All right, Bethany. Since you proposed this approach, you have to tell me, as r goes to infinity, what's going to happen to inverse tangent of r?
It's gonna converge to pi halves.
Very good. And this limit, it's actually going to go to pi over 2. Or at least just the inverse tangent of r by itself. With the idea being, we look at the unit circle, pi over 2 is up here on the unit circle. If we were trying to take a point like right here, we're trying to take sine of x over cosine of x, we can say that that's going to go to infinity as x approaches pi over 2. So in other words, as x approaches pi over 2, at least from the left-hand side, tangent of x is going to go to infinity. So if we kind of reverse that, it would make sense to say the limit as x goes to infinity of inverse tangent of x is just going to be pi over 2. Well done. All right, Bethany, how about inverse tangent of 1?
Would that be pi fourths?
Because sine of pi over 4 over cosine of pi over 4 is just 1, since pi over 4 has the same sine and cosine. So it's going to come out to pi over 4, I think. So, Rhoda, this integral came out to pi over 4. What does that tell us about our initial infinite sum?
It means it has to converge.
Yeah, so this integral converged, which is going to tell us in turn that our original infinite sum also is going to have to converge by the integral test. Because if we converted it to an integral from 1 to infinity instead of a sum from 1 to infinity, the integral happened to converge, which tells us that the sum that we started with has to be a convergent sum as well. Dr. Gerstle, why are you giving us inverse trig integral still? Can't we just leave that behind back in standard 5 where it belongs? Turns out there's another way. We could have used the integral test on this. Bless you. A sneakier way. A way that doesn't involve actually having to do any inverse trig functions. Or, heaven forbid, evaluate an inverse trig function at a variable as that variable goes to infinity. Not all of us have Bethany levels of inverse trig knowledge. I know I don't, probably. So, what would be another way that we could have determined that this integral converged without relying on actually integrating and using inverse trig functions? Should have erased all this. Kate.
Well, I would have used a comparison for this one.
Comparison test?
Yeah.
Okay, what would you have compared 1 over x squared plus 1 to?
Over x squared.
Okay. Gabe, was that going to be your idea as well? Okay. So 1 over x squared plus 1, Kate wants to compare to 1 over x squared. So which of those is going to be bigger?
1 over x squared.
Yeah, I think so. X squared plus 1 is bigger than x squared. And so the fraction with the bigger denominator is actually going to be smaller as a whole. So that's going to tell us that the integral from 1 to infinity of 1 over x squared plus 1 is actually going to be less than integral from 1 to infinity of 1 over x squared by itself. Gabe, what do we know about the integral from 1 to infinity of 1 over x squared?
It converges.
It converges because it is a,
P integral
with p
greater than 1.
equals 2 greater than 1. Indeed. Yes, this integral is going to converge as a p integral with p equaling 2, which is a value greater than 1. And so, Kate, I'll go back to you for this one. If we have an integral that's smaller than a convergent integral, what does comparison test tell us about this integral?
None of us converge.
Bingo. Yeah. So we can say since integral from 1 to infinity of 1 over x squared plus 1 is smaller than a different convergent integral by the comparison test. The integral of 1 over x squared plus 1 must also converge. And thus we can then say by the integral test once again, sum from k equals 1 to infinity of 1 over k squared plus 1 must also converge. So that kind of gives us a sneaky way to look at and actually determine whether or not this integral converges by without actually having to integrate it, or without having to actually get inverse trig functions involved. So at this point, since we spent the whole first half of the semester talking about how do you integrate different types of functions, when you have these sort of improper integrals, you may have sneaky ways to determine whether or not the improper integral converges or diverges without actually having to go through and integrate. The one advantage Bethany's method had, actually just brute force evaluating this integral, one advantage this had is it told us exactly what this integral came out to. It came out to pi over 4 precisely, whereas the Kate/Gabe method here only told us that the integral comes out to some finite number, who knows what it is. But in this case, we don't need to know exactly what this integral comes out to. We don't really care. We just need to know, does it come out to a finite number or does it diverge? And the fact that it came out to a finite number is enough to tell us that our original series had to also come out to a finite number. Questions, comments, concerns? Jonah, almost 2 full semesters later, are you still amused by my dancing antics at the front of the room? Gets the blood flowing.
Never gets old.
Oh, well, I'm glad to hear it. I'll keep doing it for you then. Okay, let's look at one more. Then I'll give you all a chance to look at a few on your own. I'm going to actually skip the next couple in the packet. And instead, let's look at a sum from n equals 1 to infinity of sine squared n over n squared. So that's sine squared of 1 over 1 squared plus sine squared of 2 over 2 squared, sine squared of 3 over 3 squared, dot, dot, dot. Jonah, what is sine of 1?
Pi over 2? No.
Sine of pi over 2 is 1, but not sine.
Oh.
Sine of 1 is not pi over 2.
I don't know.
How about sine of 2?
I don't know.
Sine of 3?
They're just like decimals, right?
Well, you're no help. Actually, none of them are nice numbers at all. I have no idea what any of those are come out to be equal to either. Sorry, that's the sort of trick question I would normally reserve for James, but he's not here, so you're my proxy, James, for today. Congratulations. So I don't even know how to evaluate literally the first term in this sum, or any of the others for that matter. We know sine of 1 is going to be some decimal between -1 and 1. Because sine of x always returns values between -1 and 1, which is how I know it's not going to be pi over 2, because pi over 2 is bigger than 1. But as to what this actually comes out to, I have no earthly idea. Nevertheless, I think we can tell, does this converge or diverge? Let's look at the corresponding integral. Integral from 1 to infinity of sine squared x over x squared. Bethany, do you know how to evaluate, do you know what function has a derivative of sine squared x over x squared?
Well, if we take out the squared of sine of x over x, then that's the like the identity thing that comes to 1, right?
That comes out to 1?
Or like, yeah. Because isn't sine of x over x 1?
Ah, we could say that a limit as x goes to infinity of that is, or we could say that if we take a limit as x goes to 0 of sine of x over x, we get a limit of 1. But that's not the same thing as saying the integral of sine of x over x, if we square that, comes out to 1. Sine of x over x is not itself always equal to 1, that's just what happens near x equals 0. Is that what you're thinking of?
Yeah, I was also confused because does the sign of 1 come to 0 or no?
Nope. So sine of 1, in a unit circle, 1 radian is going to give you a point that's like here-ish. It's probably going to be pretty close to pi over 3. So sine of that is going to be something close to square root of 3 over 2. As to what value exactly, though, I can assure you it is a very not nice number. So I'll ask you again, Evan, how do we integrate this?
Could we do the integration by parts?
You could certainly try. Eventually, you'll be able to get that into a form of needing to know how to integrate natural log of x times sine of x. I don't know how to integrate that, if I'm being honest. So I don't think integration by parts will work. Any other ideas?
Could we do the comparison test?
Compare it to what?
About 1 over x squared.
Oh, the same comparison we did last time over here? Or I should say the same comparison that your classmates did last time while you were brute forcing it? Joy thinks that was a sick burn. Okay. We wanted to take sine squared x over x squared and compare that to 1 over x squared. Alright, Joy, which of these is going to be bigger?
Since that's near pi over 3, so it's going to be slightly larger than
Pi over 3 is slightly less than 1.
oh, slightly less.
Or no, pi over 3 is, no, I take that back. Pi over 3 is greater than 1. I don't think this is going to be close to pi over 3. What I said is 1 is close to pi over 3, so that sine of 1 is probably going to be close to sine of pi over 3, which is about square root of 3 over 2.
Okay, so assuming that that's smaller than 1, then that's going to be smaller than 1.
Assuming that this is smaller than 1, that's going to be, then that over x squared will be less than 1 over x squared. Do we know sine squared x is always going to be less than 1?
Yeah.
I saw Bethany give a little nod. Gabe's shaking his head a little bit. Gabe?
But doesn't the sine function only fluctuate between -1 and 1? So it has
Ah.
to be less than or equal to 1.
Yeah. So in other words, what Kate is pointing out is that sine of x by itself is always between -1 and +1. So if sine of x is between -1 and +1, Kate, what does that tell us that sine squared of x always has to be between?
Well, -1 and 1 squared are just 1. So less than or equal to 1.
And greater than or equal to
0.
yeah, 0, because anything squared is always going to be non-negative. So sine squared x being less than or equal to 1, that's going to tell us that if we take sine squared of x over x squared and compare that to 1 over x squared, which one's going to be bigger, Kate? Or let me rephrase, should I put a less than sign here, or a less than or equal to, or greater than or equal to?
Less than.
Turns out sine squared x over x squared is always less than or equal to 1 over x squared because of the fact that sine of x is never going to be bigger than 1, so sine squared of x will also never be bigger than 1. Alright, Bethany, looks like we have our comparison. We can compare this, turns out, and say that this integral has to be less than or equal to integral of 1 over x squared. Where do you want to go from there?
So this will converge since to, the whatever x squared, the p is 2, which is greater than 1.
Yep, it's a p integral where p equals 2 greater than 1, just like we said over there on the sideboard. And therefore the original integral, which is less than a known conversion integral, is going to,
Also converge.
which tells us that our original series is also going to, bingo. Yeah, so that's going to tell us then that the integral from 1 to infinity of sine squared x over x squared converges by the comparison test, which then tells us that the sum from n equals 1 to infinity of sine squared of n over n squared is going to converge by the integral test. By the way, the primary reason I introduced the comparison test to you back in Standard 6 for improper integrals is because I knew this day would come where we would want to use it to help us determine whether or not series converge. We're not going to have it in a formal packet, I don't think, but it turns out you could also just say sine squared n over n squared is less than or equal to 1 over n squared, and use the comparison test on the series directly rather than having to convert to integrals first. Oh, also Bethany, getting back to what you said earlier, I have no idea how you would actually integrate that directly. If you had come up with something, I was going to be highly impressed. Instead of only slightly impressed. Any questions or comments about how we would evaluate these sums or these integrals? 5 minutes left. It's not really enough time to give you all time for practice problems. Let's do one more. Let's do the one on the previous page that we skipped. Let's do sum from k equals 2 to infinity of natural log of k divided by k. So natural log of 2 over 2 plus natural log of 3 over 3 plus natural log of 4 over 4, etc., etc. Well, that's very much not a p-series or a geometric series. So let's try out an integral test on it. We wanted to integrate natural log of x over x from 2 to infinity. And this time we're going from 2 to infinity instead of 1 to infinity because we're summing from k equals 2 to infinity up here. Ryan, how would you, what would you do with this bugger?
Could you do u sub and have u equal natural log of x and then u be 1 over x?
Ah, okay. We can certainly do that. So let's let u be equal to natural log of x, which would give us du is 1 over x dx. Which is going to give us what? Limit as r goes to infinity, integral from x equals 2 to x equals r of, Ronan, how would you write that as an expression in terms of u?
It would just be u.
Okay.
U be u.
Yeah, natural log of x over x is the same as u times du. Allie, how would we integrate u with respect to u?
U squared divided by 2.
Yep, we're gonna get a 1/2 u squared from x equals 2 to x equals r. Before we plug r and 2 in, we need to rewrite in terms of x. So that'll give us a limit as r goes to infinity of 1/2 natural log of x quantity squared from 2 to r. Well, that's the same as taking a limit as r goes to infinity of 1/2 natural log of r quantity squared minus 1/2 natural log of 2 quantity squared. Nolan, as r goes to infinity, what's going to happen to natural log of 1/2 natural log of r squared?
It's,
Give you a hint. Here's what the natural log function sort of looks like.
it's gonna go to infinity.
Yeah, it's going to go to infinity. So what does that mean about the original integral here? If we have a piece of it is going off to infinity like this.
It diverges.
Yeah, that means the original integral has to be a divergent integral since the integral isn't coming out to a finite number. So we can say that tells us that integral from 2 to infinity natural log of x over x is going to be divergent. And if that integral is going to diverge, then Sarah, finish this off for us. What does that tell us then about our original series?
It means that also divergent.
Yep, that tells us that the series is also going to be divergent. So moral of the integral test is, with the integral test, you take your series, you convert it into an improper integral, determine whether or not that improper integral converges using standard 6 methods, and then that tells you whether or not the original series is going to converge or diverge. Alright, that's it for standard 12. There's at least one extra practice problem in there that I'll let you all take a look at on your own. And I'll have solutions for this posted later today. And in the meantime, exam Friday, let me know if you have any questions. Have a good one.